Alrighty, so here we go. So exponential and logistic functions, emphasis on the exponential here. Definition, an exponential function, and you've seen these before, is anything, any function of the form f of x equals a times b to the x. And a is referred to as the initial value, and b is the base. Okay, so this kind of has a power function type look to it. Do you guys remember that from section 2.2, I think it was? What's the difference between what those looked like and what these look like? Yeah. X is now in the exponent, right. Those were like a number times x raised to a number. And this is a number times a number raised to x. Okay? That's the key. The x is in the exponent now. That's what makes it exponential. Okay? Okay. So, one thing that you guys are going to be asked to do is to identify if you have an exponential function or not. And if so, what's the initial value, what's the base, that sort of thing. So I'm going to give you guys a few here and see if you can tell me which ones are exponential, which ones are not. All right, let's look at those 5 and see if we can riddle it out. So like I said, first of all, yes or no, is it exponential? And then second of all, if it is, what's the initial value, what's the base? And if it's not, why not? Okay, we'll do that too. Why does it not work? So the first one, f of x equals 3 to the x. Does that fit the definition? Yes, it does. Okay, so yes on that one. Okay, so what's the initial value, what's the base? So a is equal to what, b is equal to what then? Yeah.
A is 1.
Yep, a is 1, b is 3. If there's nothing written out, multiplied in front like that, then a is just 1. Good, okay. What about the second one? Square root of x to the x. Is that exponential? Does it have an x in the exponent? Yeah, so that seems to be okay. But it's not. What's wrong with it? X is also in the base. And the base is supposed to be a what? Just a number. Yeah. So the base cannot be variable. Okay? So this is no. And the reason is it's a variable base. Base has to just be a number. Okay. Third one. Negative 2 times 2 to the x. Yes, that one works. Okay, since it is, what's the initial value for this one? Negative 2. What's the base? 2. Good. Okay. The next one, x to the 5th. Is that exponential? No. Why is it not exponential? Again, variable base. X is not in the exponents, variable base. Yeah, all that stuff. So, yeah, variable base, no x in exponent. So, for both of those reasons, that one doesn't work. Okay, and then the last one. Negative 3 times 2 raised to the x over 2. I heard some yeses. And it's true, it is. It is a yes. Okay, so let's see if you can do this then. What's the initial value? Negative 3. And be careful, what's the base? Oh, you guys are good. Square root of 2 is the base. Does everybody see why that is? Right here, I have 2 raised to the x over 2. I can rewrite that as negative 3 times 2 to the 1/2 to the x. Does everybody see that? That's a rule of exponents you guys have learned before, right? In Algebra 2 you talked about that. It's power of a power is what that's called. So if I can take that 1/2 off that x, bring it down inside, what is 2 to the 1/2 power? That's a square root, right? It's a square root of 2. So this is negative 3 times the square root of 2 to the x. So actually, even though you see just a 2 in the parentheses there, the base is actually the square root of 2. And we're going to write exponential functions that way later. When we do some modeling tomorrow, we're going to deal with having to kind of convert those back and forth a little bit like that. But yeah, good. Okay, so let's talk a little bit about initial value. Why do you suppose that the a is called the initial value? Mm-hmm.
It's what you have when x is 0.
Exactly. It's kind of that starting point, right? So when x is 0, when you have nothing, it's, well, not when you have nothing, but when you're starting, I guess, it's how much you have. So, like, for example, real quick here, if I had an exponential function f of x equals negative 4 times 3 to the x, okay, and I plugged in 0, so f of 0 would be negative 4 times 3 to the 0. And anything to the 0 power is what? 1, right? So really what you have is f of 0 equals negative 4. So that's where we get that name from, is if x is 0, the function's going to come out to that first number every time. Okay? The only thing that I would caution you with here, because if you do this, it doesn't work anymore. These two things are not the same. Don't do that. Why can I not do that? Yeah. Order of operations has something to do with it. Mm-hmm. But it's a little bit more than that, though. This right here, what's being raised to the x power? The 3. Is the negative 4 being raised to the x power? No. You cannot multiply those together unless they're both being raised to the same power. Okay? So it's just the 3. So these two, even though it looks like, oh, multiplication, they're right next to each other, I'm just going to put those together and it's all good. You can't do that. Okay? One's being raised to a power, the other one's not. So they do not go together that way. Okay? It's a very common mistake that people make. If I were to do that, then this whole initial value thing I'm talking about goes out the window too. It doesn't work anymore. So that's a big no-no. And like it is related to order of operations, though, as far as you do the exponent before you multiply and that sort of thing. So technically, you were right too. So okay, I just wanted to make mention of that. Okay, so now that we kind of know what exponential functions are, we can identify them. Can we start like building these up a little bit? So I'll give you an example. So let's find the exponential equation. That goes through zero, 3, and bless you, 112. All right, so every exponential looks like this, unless there's been some kind of a transformation done to it where it's been like shifted up, down, left, right, or something like that. But in general, before any of that kind of business happens, it looks like this. It has to go through the points 0, 3, and 112. So I need to figure out what's A and what's B. So let's start with A. Anybody tell me what A is? Yeah, it's got to be 3, right? Look at this first point that I gave you, 0, 3. So what that means is 3 equals A times B to the 0. Okay, well, what's B to the 0? 1, right? Anything to the 0, even a variable, is 1. So I end up with 3 equals A. So boom, got the first one. I know A is 3. So now I can go back to this first equation, and I'm a little further now. Now I got f of x equals 3 times b to the x. So how do you suppose I can find b now? Yeah, Josh.
X could be 1. After that, for 1 to the 12,
Mm-hmm.
X would have to be 1.
X is 1, and y is 12, right? Yeah. So 12 equals 3 times b to the 1. Okay, and b to the first power is just b, right? So it's 12 equals 3b. So what's b? 4. Yeah. So I've got a, I've got b. So now I've got my function. F of x equals 3 times 4 to the x. That's the one that works. Okay. So the graph of that thing would look something like, let's see, it goes through 3 when x is 0, and then when you're out at 1, it's up to 4. So this exponential function kind of does something like that. Okay. So does that shape look familiar to you guys? We talked about our 12 basic functions and the exponential and how it works. Oh, it's 112, not 14. Sorry. My bad. This is a lot steeper. Hold on. So this goes, and the 1 is probably like out here somewhere. Yeah, and then like maybe 12 is like up here somewhere. Yeah, sorry. I knew exactly what you were going to say. Okay, so in any event, the point I was trying to make, though, is you guys all see the shape of this thing, though, and does that jog your memory banks a little bit from Chapter 1 when we talked about exponentials briefly and what their shapes were? I said memorize the graphs for all of these guys. So they're all going to have this kind of look to them, okay? Now, depending on the values of A and B, the way that this exponential curve is oriented might change, okay? So we're going to investigate that just a little bit here, okay? So how changing the A and the B change things around for us here, okay? Well, exponentials can do growth or decay. Now, first of all, let's just assume that A is something positive for right now. Okay, we'll switch that around later. So A is positive, A is positive. If that A is a positive number, and I want my exponential to be a growth, what has to be true about the base? It has to be not just positive, more than positive. Yeah. Larger than 1. Think about that. The base is the number we're raising to the exponent. If that number is something less than 1 and I raise it to a really large exponent, what's going to happen to the value of it? It's going to go down, right? If you repeatedly multiply a number that's less than 1, it's going to get smaller and smaller and smaller and smaller. It's going to create a decay. But if that number is bigger than 1, then you're multiplying by something again and again and again. That's going to cause this thing to grow as you do it. So to make a growth, again, as long as A is greater than 0, B has to be greater than 1. And a decay, like we just said, B has to be less than 1. But it can't be any smaller than what? 0. If it's less than 0, it's actually not even exponential anymore. So it works kind of like that. If it's a growth, if the A is greater than 0 and the B is greater than 1, yep, kind of like the last one we just looked at. If A is greater than 0, then the B is between 0 and 1. That's going to create a decay. All right. So, yeah, this is all the A greater than 0 stuff. Now, what if I switch that around, though? So what if A is a negative? Well, then it's exactly the opposite. If the base is between 0 and 1, it's actually going to grow. And if the decay, or if the base is greater than 1, it's going to decay. All right? And I'll show you a quick sketch of what each of these different situations looks like so you can kind of see what's going on. And there's some connections between them, too. Okay, so this first one, where you have your base is greater than 1, A is positive, that's going to create a graph just like the one we looked at with that example we did. It's going to do something like this. If that base is between 0 and 1, but A is still positive, then it's going to do something kind of like this. Okay, so growth, decay, right? Now, if I let A be something negative, think about this for a second. This actually relates to something we've talked about before with transformations. If I stick a negative in front of a function, which is essentially what I'm doing when I make A negative, right? What happens to the graph of a function if I suddenly just make A negative? It doesn't move it down. It reflects it down, right? It reflects it over the x-axis. Okay, so this one right here, do you see how this growth and this decay are pretty much the same thing, except now A is negative compared to being positive? So this graph here, this one we're about to do, is the exact same thing as this one, just reflected down over the x-axis. So it looks like this. Okay, so do you see how a reflection of this second one down to here turns a decay into a growth? Right, because it's actually increasing as it goes. Okay, so this is actually a growth. That's why that opposite thing works, where the decay kind of becomes a growth and the growth becomes a decay. So this last one, then, it's the same kind of story with the first one, then. It's a reflection of that first graph over the x-axis. And so it looks like this. Has that kind of a shape to it. All right, and each of these has A as your y-intercept, because it's that initial value, right? We said when x is equal to 0, that's where A is. Take a look at the first two. For the first two, isn't A positive, right? We said for both of these, this is when A is going to be bigger than 0, so those are both positive. Over here, we said A is going to be less than 0, so those are both negative. Okay? So again, that initial value, it's when x is 0, it's a y-intercept. On the graph, you can kind of determine where those are at that way too. Okay? So, now the question becomes, can you sketch a graph of one of these for me then? So if I give you an exponential equation, can you determine which one of these four categories it falls into and sketch what that graph should be? So we'll try a couple of those and then we'll move on, but let's see if we can do that. All right, so let's try this one. So sketch the graph and then indicate, is it a growth or a decay? Because part of your homework, they're going to ask you just indicate if this is a growth or decay. So if you can graph the thing, then you can look at it and just answer the question then. All right, so -2, 1/2 to the x. So which of these four categories does it fall into? Is it 1, 2, 3, or 4? So A is negative, right? And B is between 0 and 1, so it's the third one. So it should be a growth. We should be getting a growth here. Okay, so it's going to look like this. Okay, and this y-intercept should be what? -2. Yeah, we know exactly what the number is this time, right? Based on the equation. So that should be at -2. So something kind of like that. All right. It's increasing as you go across it, so this is a growth, just like up here says it should be. Got it. Okay. Let's do another one. So what did I do to this one? Added a constant on the end, this +1. So what's that going to do to my graph then? It would be what? It moves the y-intercept which direction, up or down? Up 1. Okay. So what I would do is start with just sketching the thing before you do the +1 on the end of it. Okay, well, you know it should look like. And then you can just scoot the whole thing up 1 unit, and you got it. All right, so which category have we got here? 1, 2, 3, or 4? It's the second one, right? It's got A is positive this time. B is between 0 and 1. So this is a decay. And so initially, it would look something kind of like this. Okay? And that y-intercept before it's been shifted up would be what? 3. But what is it actually going to be now? Moved up. Should be at 4. So it's going to look like something closer to this. With that y-intercept actually now up at 4. Okay, so you're going to be asked in your homework to do some matching of some graphs and that sort of thing, and it's going to have some translations thrown in there too. Okay, but don't let that throw you off. It's just taking these 4 shapes and then just shifting it up, down, however much, if they happen to add something on the end of it there. And yeah, that's it. Okay, so I actually want to do one more of these just to show you something else you might come across. That's actually still exponential as well. And this is one you're probably going to want to rewrite in a different way to be able to match it up with what you have. Okay? What do I do with that negative x? How could I take that and like change my base to something else? Yeah.
Can't you like make it a fraction and put the x in the bottom?
Exactly. Well, you don't know. You don't put the x in the bottom though. I guess you could, but we don't want to. So in any event, I like the fraction though. So 1/2. If I was going to strip the negative off of that x, this would be 3 to the negative 1, right? Kind of doing that power of a power trick like we talked about before with the fraction, okay? But what is 3 to the negative 1? No. It's 1/3, right? It's not negative 3, it's 1/3. So what we actually have here is 1/2 times 1/3 to the x. Okay. So to sketch that then, we have a is greater than 0. Our base is between 0 and 1. So this is going to be second category again, right? B is a fraction. So it's going to look like this. And what should be that y-intercept? 1/2. Okay, so I just wanted to show you that because I remember last year I didn't do this example and there was a negative x, actually there's several of them in there, and that threw some students off. But that's all they're talking about though. Okay, it's actually exponential still. Negative x is just another way of writing a fractional base in that way. Okay, so exponential I wanted to look at with you guys. Let's quickly talk logistic and then we'll be done. All right, make sure that's still on there. Okay. All right, so a logistic function. Two different ways they could be written, depending on how you're going to do it with what base. We'll probably stick with this one for the most part. So it's c over 1 plus a times b to the x. Now, logistics and exponentials are kind of closely related. Do you see the exponential function that's been kind of just stuck in there? That little a times b to the x is part of that. The c is called the limit to growth. Okay, here's the difference. With exponentials, and this is just assuming like the basic exponential, everything's positive, b is greater than 1, yada yada. Exponentials do this, and they just keep going up, right? Doesn't do that. It grows like an exponential, but then it levels off eventually. It does something like this. So it heads up, and then it says, nope, I'm not going to keep going. Going to level off like that. So it starts to look exponential, but then it stops. Okay? And logistic functions are useful because when we get into modeling tomorrow with functions, the way like populations work, most people assume that populations are always exponential. Have you heard that before? That populations always grow exponentially. They just keep getting bigger and bigger and bigger and bigger and just keep going off. Technically, that's not true. We have a finite amount of space on the earth, right? Or like animals in an animal preserve or whatever, have a finite amount of space. Okay? There are so many animals you can fit in there. Okay? Whether it's just physical space or it's the animals are going to naturally start like killing each other off or whatever. Humans, you could say the same thing, I guess. But anyway, there is a limit to the growth, right, that we can have for any population. There's always a limit to how big it can get. So do exponential models make sense in that kind of a context? Not really, right? We can't just keep going. It's got to level off somewhere. So real population models tend to be logistic, not exponential, because there's always going to be like an exponential looking type growth, which, most populations experience, but then there's always this leveling off point at some point down the road. So, in fact, almost every single population of any animal on Earth is, if you look at it over a long period of time, is logistic. There is only one animal on this planet that has not grown logistically yet. What animal is that? Us. People. We are consumers. We're taking over the planet and we're just going up. Now, actually, like I said, there's only a finite amount of room on the planet. Can't keep doing that. Maybe we'll fly off to Mars or something. I don't know. But in any event, if we're staying on the planet, eventually we are going to become logistic too. Right now, like if this was a population of humans, we would just be simply right here. Like maybe this is, 2014 or whatever on the curve. We haven't leveled off yet. Ours is coming. Eventually we will. But right now we look exponential. Eventually we will be logistic just like everybody else. But in any event, in the actual equation that gets used here, yes, C is the limit to growth. Okay, and it's this horizontal asymptote that we're leveling off to. That's C. Okay, so this Y value up here, that's C. So we always start at 0. There's two horizontal asymptotes for every logistic. There's the x-axis, which is y equals 0, and then there's also y equals C. Okay, so maybe we'll jot that down too. Okay, and then there's always this mistake that students make with this too, where I ask them, okay, here's a logistic function. Tell me what the initial value is. And they go and they find the a in there, just like the regular exponentials, and say, oh, there it is. I found my a. That's the initial, just like with exponentials. And it ain't the case this time. Plug in a 0. If I plug in a 0 right here, I get b to the 0, which is 1, so it's gone. But then what's left over? There's still 1 plus a down there, right? And don't forget about the c. That's still there too, right? So the initial value of a logistic is actually c over 1 plus a. So the initial value, or y-intercept technically, is c over 1 plus a. And really, just plug in a 0 if you're going for that. That's all you're doing, is just plug in a 0. So, all right. So let's see if we can analyze a logistic function here. Okay, so how about f of x equals 2 over 1 plus 4 times 2 to the x? So what's the initial value? And what's the limit to growth? Let's start with that because we've already talked about both those two things. And I bet both of those two you guys can do in your head here real quick. Okay, so what is the initial value here? 2 over 5, right? because this would just be 1 plus 4 after this goes away, so 2 over 5. And what's the limit to growth? 2. Good. All right. Let's see if we can find some other stuff here. Now remember, this is the graph of it. If every logistic kind of has that shape. What are my x-intercepts? None. Good. It never crosses the x-axis. We already did the y-intercept. How about horizontal asymptotes? So for this particular function, what would be its horizontal asymptotes? Yeah, y equals 0, y equals 2, and then, since I got a little room here, what would be its vertical asymptotes? Yeah.
Wait, how do you know the x-intercepts?
How do I know there are none?
Yeah.
Because every logistic looks like this, and there's always a asymptote down here, so it never actually comes down and crosses it. So it's always stuck above, kind of like that one. So vertical asymptote, there's none. Yeah, every logistic, that's the case. There are none. Okay, and it's all because of that horizontal asymptote of y equals 0. It's never going to get down past that. It just kind of comes down and approaches it. So you'll never have an x-intercept. You'll never have any vertical asymptotes, anything like that. Even though it is a fraction, okay, getting this denominator to come out to 0 is not going to work in its basic form like this. So you're stuck. So good. All right, so can you go the other way with it then? If I give you some information about a population, can we make a logistic function? And if we can do that, then I'm going to be done. So let's say we got a wolf population. Begins with 20 wolves in a preserve. The preserve can hold a maximum of 200 wolves. And after 1 year, there are 40 wolves. So write a logistic equation to model the population as a function of time in years. Okay, I'll give you a second to write all that down. So there's some information in there that hopefully you're starting to kind of connect with what we talked about with how these logistic functions get put together. And that's going to help us get to an answer here. And I'll go ahead and copy down your basic logistic equation here. All right, so take a look at that paragraph of information there. I already know one of my A, B, or C's. Which one do I know and how much is it? C is how much? Right. It's a good place to start. We know C is 200. Okay. What other information did I tell you that might be kind of helpful here to get started? Yeah.
C divided by 1 plus A equals 20.
All right, so that initial value we said was 20, right? 20 wolves there to begin with. So C over 1 plus A should equal 20. Can I put those two pieces of information together somehow? Figure something else out? What can I find now? A, right? So we know the C, so just plug that right in. 200 over 1 plus A equals 20. Okay, so it's going to take a little bit of work to solve that, but I think we can do it. How am I going to solve that for A? It would be a logical first step here. Okay, multiply that denominator up out of there. 200 equals, and I'll distribute 20 plus 20A. Okay. So then what? Subtract 20. So 180 equals 20A. So if I divide, what's A? 9. Okay, so I got C. Just got to find B now, right? So let's write down what we've got so far into our equation here. So f of x equals 200 divided by 1 plus 9 times b to the x. How am I going to find b? Plug in 40 and 1. Well, what goes where? What's the x? What's the y?
Y equals 40 and 4.
Yeah, the y is 40. Okay, that's the f of x, or the y, is the population, right? How many? And the x in this case is time, because we said it has to be a function of time, so x is serving as time here. So yeah, let's do that. We'll plug in and then solve for b. So 40 equals 200. 1 plus 9 times b to the first, b to the first power there. So we've got 40 equals 200 over 1 plus 9b. So we're kind of in a similar situation as with the A thing there. I got to solve this for b, but we can kind of approach it the same way, right? I can just multiply this denominator up over to the 40. So we'll have 40 plus 360b equals 200. Subtract the 40. So 360b equals 160. And then what is 160 divided by 360? 0.4 repeating. All right, so we'll just say 0.44. All right, so this thing all put together then, it's going to be 200 over 1 plus 9 times 0.44 to the x. Okay, so yeah, just chop that off a little bit, but that works. So that should model our wolf population in the preserve here. So given a certain time, plug it in, I can figure out what the population is going to be. So, okay, homework. Let you guys get started on that then.